Yeah, no assignment slide. And I hate to jinx us, but I just don't imagine this is going to take us a full 50 minutes, but we'll see. So, what's that?
You say that like it's a bad thing.
Well, no, I say that like I don't want to jinx us, because I think it's a good thing too. Which actually reminds me then, Wednesday, when we're here, we're gonna, if you have calculators that you like to kind of punch during class, Wednesday, we're going back to numbers. Okay, Wednesday, we're going back to concentrations and
So
stuff.
I'll go back to doing my homework.
What?
I'll go back to actually doing my homework.
Okay, yeah. I don't know what to say to that. Okay, so you guys know the whole matter can either be a solid, liquid, or gas. We've talked about intermolecular bonds. We've been kind of talking about breaking those bonds and forming those bonds and things like that. I want to focus on solids and then kind of basically talk a little bit about melting, which is something going from solid to a liquid. So that's kind of why this was put together. So this is, I think, I put together this sheet to kind of make sense of this lecture, because I was like, what in the heck? So first off the bat, solids can be either a crystalline or amorphous. And if you look at the thing I gave you, that's like the first layer. Okay, crystalline or amorphous. Okay, now we talked about the crystalline lattice structure, and as it turns out, I think he's jogging in here. As it turns out, there is, if you look under crystalline, we have ionic crystalline solid, we have molecular crystalline solid, network, and metallic. So of these two, amorphous and crystalline solid, which one are we going to talk more about? Crystalline, yeah. Now, amorphous rocks, isn't that where they're kind of, just kind of ooey gooey melted and, yeah. Where does he sit? Is it here?
Does amorph mean without shape or something?
That sounds right. Not well defined. Yep, without shape. Okay. So crystalline solids, what else do we need to know about crystalline solids? Well, before we get there, kind of left and right. Actually, plastic, okay, any sort of poly whatever is, hi Mike, is an example of an amorphous solid, okay? These over here are examples of crystalline solids, okay? So you might recognize like sodium chloride. This is solid aluminum metal, okay? And it's funny, you're gonna have to switch gears a little bit because I have never used the word crystalline when I talk about solid metals like that, but it is. It's very orderly. Then up there we have silicon solid.
So are crystalline solids, are they generally not very bendable, like they're not very
Right.
malleable solids?
They are,
They're just-
yep, crystalline solids oftentimes are not malleable, they're just, although that's not true because
Aluminum is bendable.
aluminum's
Yeah, that's what I was
bendable.
thinking.
Yeah,
Okay.
yeah, aluminum's bendable.
So it's just more than on like the molecular level.
Yeah. That's a good point. And we'll talk a little bit about the temperature at which you need to liquefy, how that works. So, make sure we're all on the same page here. So crystalline solids, we're starting with molecular crystallines. Now you see kind of molecular and ionic, we've been talking a lot about compounds, either being a molecular compound or an ionic compound. Do you remember I said if you can find a nonmetal, then that compound must be, which one? If you can find a nonmetal.
Say that again, what you
If you can find a nonmetal in the formula for that compound, that means the compound must be molecular. Then it must be molecular, because you must have somewhere in that, we said we have electrons are being shared. Yep. So molecular substances can be stuck together by dispersion forces if they're nonpolar. Okay, they can be stuck together if they're polar by, that would be ordinary dipole. If they have an oxygen, nitrogen, or fluorine that's connected to a hydrogen, they can be stuck together by intermolecular bonds that are hydrogen bonds. In general, and this is where I kind of went down here, okay, in general, regular intermolecular bonds. In general, I guess I could, if I was you, if you want to, you could put down here, you could put this stuff. You could say molecular crystalline substances are generally soft, low melting, and they do not conduct electricity. So again, we're talking about the substances all in their solid state. Because I was going through this before and I'm like, I just got lost at what slide was what. But if you look at it like this, it's really not all so confusing. So that was molecular crystalline solids. Now I'm going to, there's water. You recognize the red is the oxygen and the white are the hydrogens. There's water in its solid state, all bonded together with hydrogen bonds, right? Crystalline solid. Now we're going to skip to the network. So again, where is network? Well, it's over here. It's under the crystalline solid network. Okay. Now these are going to be actually, I want to say atoms. Is this right? No, I'm not going to say that. Atoms of the same, yeah. Not necessarily. I was going to say they're all atoms of the same type that are joined together, but I think actually this is when silicon dioxide, I think, is a network solid. But they're joined by covalent bonds. Electrons are shared. With regard to, they're hard. With regard to melting point temperatures, they're pretty darn high melting point temperatures. We're going to see melting point temperatures, not as good as boiling point temperatures, are kind of showing you the intermolecular bonds. Okay, so we skip to network. I have some examples here. Remember we talked about I love some of these words in chemistry, physical science, allotropes. Okay, allotropes are basically different forms of the same substance. Like, for instance, one allotrope of carbon is graphite. Okay, another allotrope of carbon is diamond. So this is an example of network solid. This is carbon again, as it exists as a diamond. Those dashes and the dashes before were covalent bonds. Probably why they're kind of would we say the high melting point temperatures? All right. I'm not going to show you the buckyball, but yeah, here's the silicon dioxide, quartz. Okay. So quartz has, for every repeating unit, bless you, it's one silicon and two oxygens, okay? Now, if you try to find it up there, it looks like we got silicon is white and the oxygens are red. I guess we had it before. In this case, so you can kind of see the central silicon atom, but it's like, it's like a crystalline lattice structures, but there's no ionic bonds there. Those are all covalent bonds. So I think that's kind of fun. One repeating unit of an SO2 molecule. It's kind of hard to get when it's in its solid state like that. All right. Now we skip back to ionic crystalline substances. So this is actually finally, when I talked about the two types of compounds, I actually used the word crystalline when I talked about ionic substances. Okay. Now finally, for ionic compounds, you need to have maybe I did say that wrong a little bit ago, Rhonda. If you have all nonmetals, it's a molecular compound. But ionic compounds is one nonmetal and one metal, so I kind of didn't, yeah, that's why I kind of threw you off. So ionic compounds, remember, has a metal, and the metals are great at losing electrons. They form cations. So you have a transfer of electrons, and then you have that dot, 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 that intermolecular bond that actually is more of a chemical ionic bond, is what I think of it. In our list of 6 different types of intermolecular bonds, ion-ion was the strongest. So not so surprising, maybe, these are the highest melters. And though they don't conduct electricity, and we'll talk more a little bit about an electrical cell at the end of Chem 2, but electrons don't flow freely through them. If you dissolve them in water, then electrons can flow freely through them. Like getting electrocuted in, no, this is not right. If your water is pure, it won't conduct a current. Okay, but it being pure is not something I'm willing to take.
If you
Chance on.
don't mind me saying so, my hydrogeology professor told us that if people drink only distilled water, they end up losing minerals because
Oh.
the water seeks to pull minerals from the bones to keep a ionic balance of some kind. Does that
Interesting.
make kind of sense?
So you count, that makes sense.
What, UFC fighters, when they're cutting weight before fights, they drink, what is it?
Distilled water?
Distilled water for like 2 weeks beforehand because it causes them to cut weight. It actually
That's not
dehydrates
good
your
though.
body.
That's not good. Interesting. It pulls things that shouldn't be pulled. But the fact that there's that big of a difference between tap water and makes you wonder what's in this, you know? Huh. Interesting. Cool. Well, the one we haven't talked about is actually my favorite. Oh, actually it's coming up. Okay, so that's sodium chloride. The swollen ones are the chloride ions that have picked up an electron. The small ones are the sodium atoms that have lost an electron. And there it is, kind of backed off. So back in Chem 1, I called this a crystalline lattice structure. And now actually we're kind of finding that it's not the only crystalline structure out there. Okay, so the last one we didn't talk about are the metals. And this is where all of the atoms are this, well, actually you could have multiple metals. But these are all just metals that are stuck together. Now, one of the things I think I maybe said before is like stainless steel is a metal of different grades that has different metals that are frozen in a solid we call stainless steel, right? And that's actually it's usually a homogeneous mixture, but there's no chemical bonds between those. But here I'm saying, yeah, it's not ordinary covalent bonds. So, do you guys remember what's that?
Carbon atom.
Oh, come on, people.
Hydrogen.
Is that a hydrocarbon?
It is a hydrocarbon. Starts with letter B.
Benzene.
It is benzene, yep. So we have pi, sigma, pi, sigma, pi. And the reason benzene actually can be drawn like this, and if you go on and take organic chemistry, actually we will call that the pi electrons are delocalized. So pi electrons delocalized, okay? What does that mean? It means that the pi electrons are just kind of being shared with those 6 carbons, okay? So I guess in that sense, this idea of if I have a piece of metal, it's not all metal, but let's just pretend like it's silver, like metal. Okay, say this is a chunk of aluminum, okay? The aluminum, let's see, aluminum atomic number 13, lucky number 13. So it actually has 13 electrons. Now, how many valence electrons does each aluminum atom have? What do you think? You guys remember? How do you get valence electrons? 3, yeah. It's got 3 valence electrons. So the 3 valence electrons for all these aluminum atoms are basically kind of delocalized. When you dislocate your shoulder, it kind of becomes no longer part of the shoulder. So they're just kind of a sea of electrons going amidst all of these aluminum atoms. So metals, we talked about this. Are they bendable? Bendable means malleable. Ductile means you can draw them in a line. Okay. Generally, they are. Their melting points vary greatly, and their hardnesses vary greatly. Now, they do conduct electricity, and this kind of makes sense. I love it when things make sense. So those 3 valence electrons are on each aluminum atom. They're basically a sea of electrons that can help a current flow from point A to point B. It's so cool. Okay. They're also pretty good thermal conductors. So think of those pluses as being, in the case of aluminum, think of those pluses as being the aluminum nucleus and 10 electrons. Okay? And then those negatives are actually then the 3 the 3 valence electrons of aluminum. Just kind of thrown out there. I just think that is so cool. Okay, maybe it's just me. Okay, so I think we covered it all. So we talked about solids can either be amorphous or crystalline. If they're crystalline, these are your 4 options. Okay, and I'm going to come back to amorphous at the end here. But let's talk melting point temperatures. So if you were going to take a solid, we talked about in Chem 1, if you're going to take a solid and make it go to a liquid, okay, of course that's an endothermic process and you need to add heat, right? And it's kind of like we've been talking about liquid going to a gas. We've spent quite a bit of time about this vaporization thing. You add heat, and we said that how much heat you have to add in order for something to gasify is an indication of the intermolecular bonds. So also, to a certain extent, how much heat you need to add to liquefy something is also an indication of the intermolecular bonds. I'm going to show you here in a minute, I think we got time for a little video from a YouTube video that shows somebody actually taking a melting point temperature. Now the reason melting point temperatures are so important are 2 reasons. 2 reasons, I think. Maybe just one. Well, the temperature at which something melts is an indication of what it is. Say you have 2 white substances, one melts at 80 and one melts at 20. You take a melting point temperature and you know which one it is. It's to identify it. The other thing actually is purity. In pharmaceuticals especially, you don't want to go, you really have to put forth a product that is sometimes just as pure as you can get a solid to be. And what we see with melting solids is if it has a wide temperature range to melt at, that means it's very impure. So say something melts at 60, supposed to melt at 60, and you get it starting to melt at 53 to 60. That's 7 degrees. That's an indication of extra stuff you have in there. Okay, actually it lowers the melting point temperature. That's right. So anyway,
Is there something that raises it too?
what's that?
Is there like an impurity that would raise the melting point also? Or is it just if it melts earlier?
No, it's all, we're going to talk about colligative properties, and just the fact, it could be any impurity, just the fact that there's anything in there in the crystalline structure, it makes it melt, I think, at a lower temperature than it really should be. Yeah. What was your question? Is there a way to, yeah, nope, nothing will make it melt at a higher temperature. But it'll give a broad temperature range. So this little video, take a look.
So isn't
Ice is held together as a solid.
steel's a combination of 2 metals, right? I forget what
Multiple, it could be, yeah.
So, but the melting point of steel will always be the melting point of whatever that lowest.
I'm betting that it depends on what you've combined to, because isn't there different grades of steel and you can have different, it just kind of depends on what you have connected together to what temperature it melts at.
So I was just going what he was saying with the impurities would raise the melting
Yeah.
point. So would it always be whatever the lowest melting point is where it'll melt, or?
It might depend on
Yeah.
how much of what specific is in there.
Yeah.
So if you have a metal that goes lower and one that goes higher, if you have more of the higher, I would assume it'd be a little bit.
Is that how that works? Or?
Well, I think,
Could it run in the middle too? If you have stuff that's really low and stuff that's high, it's kind of like.
yeah, that's kind of what you were saying, right, Mike? It would never go, it kind of,
Yeah, like where would, I guess where would it, does it depend on the composition of, like if you're mixing 2 metals to form steel, and it's 80% A and 20% B,
I
would
think
the melting point be at that?
I think the difference between, like if you have, say you're making aspirin, and you know the melting point temperature of aspirin, aspirin's a cool little molecule. Say you accidentally got some, I don't know, some calcium chloride in there, okay? So you have aspirin in the majority, calcium chloride is the impurity. So it's going to have a broad melting range. Now, in that case, think of aspirin, the molecule, and think of sodium chloride, the other molecule. They aren't interacting. There's no intermolecular bonds. Now, in the case of steel, where you have purposefully developed the right characteristics that you want, taking the metals to combine, you have made a homogeneous mixture, and you actually have you have this odd sort of, it's kind of a covalent bond with free electrons flowing. So you have created something, if it's a homogeneous mixture, that now is connected. It's not like your mixture that can be separated, and it can be separated. But I think you'd have to gasify it and then distill it. I don't know. I think it's different. I think I envision the atoms, the metals that make your steel different than the impurities when you're like the slide I'm going to show you.
Yeah.
But I see where you're going with that. And I think back to your thing is if you get like let's go back to the aspirin and what did I say, calcium chloride. Let's say instead of like 95% aspirin and 5% sodium chloride, let's say you have a 50-50 and you kind of mix that together. And we'll be talking more about the colligative properties, but I think you have something a little different there then, where it's just kind of a small impurity. So I don't know if that helps, but I think we're kind of talking about different things, but good things. It's interesting. Makes me wonder.
Yeah, I wasn't thinking of, since it's an impurity, it wouldn't be like, with the steel, it's all mixed together where it's like forming bonds. With the impurity, they're not really bonded together.
Right, because like if you're taking aluminum and magnesium and I don't know, iron, those three things, and you look at the melting point of aluminum, the melting point of magnesium, the melting point of iron, I just don't think that if you make steel out of those, that now the atoms are, I don't know, I don't think it translates into individuals versus the mixture. I don't know. You got good questions. Now let's go back to something easier. Of course, our cute little water molecules.
By hydrogen bonds. When ice melts to liquid water, the regular, relatively open structure of ice collapses. Liquid water can be more efficiently packed and denser than ice.
So so of these, let's make sure we're on the same page. What do you think? What sort of solid did we just see break? Which of these four? What's that?
Molecular.
Yes, yeah, exactly. In fact, water is underneath there. Okay. Oops. Okay. Good questions. Okay, so here's where I say melting point is not as good a measure of intermolecular bonds as the boiling point temperature. So over here, I know it's kind of hard to see that, but I could put BP temp, okay, and I could put MP temp. Okay. We talked about how the types of intermolecular bonds were paramount to indicate what temperature something's going to boil at. The stronger the intermolecular bonds, the more the intermolecular bonds, it jacks up the boiling point temperature. So also with melting point temperature, but I'm going to show you a good example of actually symmetry comes into play. You're like, what is symmetry? Well, I'll try to show you an example of symmetry. Now, I'm not going to be able to we're not going to be able to hash out all the ins and outs of this, but I just kind of want to show you an example. Before I show you an example, I want to show you these two.